In this lecture, we look at limit laws and continuity. Earlier, we used a calculator to estimate the limit as x approaches 2 of this quotient. We can do this computation more quickly without a calculator if we think about some basic arithmetical operations and their impact on our limit computations. For example, as x approaches 2, we would expect that x times x should approach 2 times 2. So the limit of x squared as x approaches 2 should be 4. We might think of this as a natural product property of limits. If we know the limit of two functions, then the limit of the product of them should just be the product of the limits. So we agree that the limit as x approaches 2 of x squared should be 2 times 2 or 4. In the same way, we might expect that the limit as x approaches 2 of 3 times x should just be 3 times 2 or 6. If x approaches 2, then 3x should approach 6. Again, the limit of the product is just the product of the limits. If the limit of x as x approaches 2 of x squared is 4, then we might expect that the limit as x approaches 2 of x squared plus 4 should be 2 times 2 plus 4, which is 8. If x goes to 2 and x squared goes to 4, then x squared plus 4 should go to 4 plus 4. The limit of the sum, or the difference, should just be the sum or the difference of the limits. If I'm adding, I should be able to just add my limits. If the limit as x approaches 2 of 3x is 6 and the limit of x squared plus 4 is 8, then we might expect that the limit of a fraction, 3x over x squared plus 4, should just be the quotient of the limits. If 3x goes to 6 and x squared plus 4 goes to 8, then 3x over x squared plus 4 should go to 6 over 8. In other words, the limit as x approaches 2 of this fraction should be 3/4. We discovered this in an earlier lecture when using a calculator. Now we have done this just by algebra and some basic properties of the limits. The last property we used here is that the limit of the quotient is just the quotient of the limits as long as none of the denominators are 0. These limit properties are fairly natural. They're common sense. The limit of the sum should be the sum of the limits. The limit of a product should be the product of the limits. As long as none of the denominators are 0, the limit of a fraction should be the fraction or quotient of the limits. Again, these limit properties are natural. They're what you would expect. For many computations, as long as the denominator is not 0, we can then find the limit just by plugging in x. The simple computation will involve sums and products and division as long as the denominator is not 0. For this reason, a problem like the limit as x goes to 2 of 3x over x squared plus 4 is an easy one. Don't use a calculator. Just plug in x values equal to 2 and you should get 3/4. The most important and interesting limit properties, however, occur when one cannot just plug in the desired x value. Earlier, using a calculator, we guessed that the limit of this fraction was 2. When we plugged in values of t close to 1, the fraction was always close to 2. Can we just plug in to this thing, just as we did in the earlier problem? Can I plug in t equals 1 and not use my calculator? Almost. Notice that if we plug in t equals 1, we get a 0 in the denominator. However, there are ways to get around this. So what is the limit of this fraction? If we just plug in, this function is undefined at t equals 1 because the denominator is 0. But if we're willing to use some algebra, we can simplify the expression for f of t. Notice that if we factor the numerator, it becomes t plus 3 times t minus 1, while the denominator is t plus 1 times t minus 1, and that this function f of t is almost the same as the function g of t. If we cancel out t minus 1 in f of t, we get g of t. And we can cancel out t minus 1, or divide by t minus 1, as long as t minus 1 is not 0, as long as t is not 1. The functions f of t and g of t are the same, except at t equals 1. It should be stressed, the functions are not the same. One of them, g of t, is defined at t equals 1. We can plug in t equals 1. The other one, though, if f of t, if you plug in t equals 1, it's undefined. These functions look just like each other, except at t equals 1. In fact, f of t, we broke it up this way. It's almost the same as this function, but they're not the same. Let me stress that with a graph. Here's the graph of f of t. It has a hole at t equals 1 because if you plug in t equals 1, you get a denominator of 0. Here's the graph of g of t. The hole is missing. We can plug in t equals 1. Graph of f of t, graph of g of t, graph of f of t, graph of g of t. See that? Only difference. These graphs agree at all the points except t equals 1. Now our limit computations, as stressed earlier, deal only with t near 1 and not at 1. So we don't care whether we're working with f of t or g of t when we're computing a limit. So after this algebra, it's easy to compute the limit of g of t because it's defined at t equals 1 and it's continuous there. So I can plug in t equals 1. So if I have to take the limit as t approaches 1 of f of t, I factor it. I cancel out the t minus 1 and get the new function g of t, and then I just plug in, and I get an answer of 2. Using algebra without a calculator, I can compute the limit as t approaches 1 of f of t by simplifying the expression and noting that since I'm not really evaluating it at t equals 1, then the limits are the same. Here's another example. Let's use algebra to compute this limit, which has an absolute value sign in the numerator. Note that as we're approaching 0 from below, we're using negative values for x. And if x is negative, then the absolute value of x is minus x. Let me stress, if x is negative, minus x is positive. So the absolute value of x is the positive minus x. So as long as x is negative, I can replace the absolute value of x by minus x and write that this limit I'm trying to evaluate is really this limit. I replace the absolute value of x in the numerator by minus x, but minus x over x is just 1. So now I'm looking at the limit of minus 1, and minus 1 is always minus 1. So there's my answer. Continuous functions are an important type of functions in mathematics. Most functions we will study in calculus will be continuous, at least in large intervals. We can loosely speak of a function as being continuous if the graph of the function can be drawn without picking up our pencil. For a continuous function, the limit as x approaches a is the same as f of a. That is, we may compute the limit by plugging into the appropriate value. Continuous functions have the property that the limit as x approaches a is just what you get by plugging in. A continuous function goes where it's expected. Its value at a is the limit. The continuous function approaches its value. There's no break or jump or singularity in the graph of the function there. The continuous functions are exactly those for which limit computations are easy. Our goal in the algebraic computation of limits is to use algebra to rewrite an expression so that a singularity is removed and we are left with a continuous function. If the function has a jump at a point, then it's not continuous. It's discontinuous. Sometimes it's convenient to talk about continuity from the left or right from a single direction. In this case, we say that a function is left continuous at x equals a if f of a is defined and the limit as x approaches a from below exists and it's equal to f of a. A function is right continuous if f of a is defined and the limit as we approach a, this should be from above, x approaches a plus, exists and its limit is the same. Most of the time we don't worry about left or right. A function is continuous if it's both left and right continuous. More precisely, a function is continuous at an x value a if the function is defined there, if the limit's defined there, and if the limit of the function is equal to the function value. In other words, the function obtains its limit at that point. We say a function is continuous in an interval if the function is continuous at every point in the interval, and there are many functions that are continuous everywhere. Polynomials are continuous everywhere. Rational functions are continuous everywhere that the denominator is not 0. Exponential functions are continuous everywhere. The sine and cosine functions are continuous everywhere. The standard trig functions are continuous at all points where they are defined. All of these functions being continuous means that when we take limits of them, we may simply plug in the value a. In some upcoming presentation, we'll look at some interesting limits involving trigonometry.